Swayam Prabha. Digital India. Educated India.
So here what happens is if you uh, this is this particular configuration can allow you to connect up to 16 Forza 64 of them, right? So if you have more than this, then that this number of switches will have to increase, edge switches as well as core switches, they will have to increase. So this configuration is shows that maximum of 16 into 4 these many can be put in. Okay, so that is what it means. And in practice you may not have all 64, you may have some free spaces if available, then you can add it. But the moment you cross this 64, then you will have to add edge and core switches. Okay, this is about the tree structure. Now coming to torus. Okay, what will happen is suppose you want, now this has got a 9. 9 is a square of 3. Okay, so we have a 2D torus with this one. Where it went? 1 minute. This one. So this 2D torus has got we will can accommodate, ideally it will have 4, 9, 16, 25, these kind of things you will have, that will give you the optimum capacity. But suppose instead of 9, uh, if you have 8, then obviously let's say mm, then obviously one of these will be missing. Let's say this is missing, then this torus will have only 2 elements, others will have, so it will be like that, this will have 2, this will also have 2, and others will have 3. So this, it will have to be made like this. Suppose now you want to, already 9 are there, you want to add a 10th one, then obviously it will remain in only one ring. Okay, because it has no companion in other rows
Yes.
and columns, it has got only a companion in a row. But if you add, instead of 10, if you make it 11, then these two rows will have fourth element and they can form a ring. So like this, you have to think of that strategy. And but point is that breaking the ring and making it is physically very much possible, but your reconfiguration of the tables is required. So that you have to do it properly mathematically, and through a program you will have to build up those tables depending upon how many nodes you have added. So that is how it will happen. Does it answer your question?
Yes. Yes, this is right for Taurus, but in case of factory, if we want to add, so in that case, we consider that we are adding to the leaf nodes. If we want to add somewhere in between, so what will we do?
No, no, see, it is like this. Like here, these are only the nodes. Nodes are always here. Okay.
Yes,
You
sir. If we
cannot add
want, let's
anywhere
suppose
else.
add if we want to add edge switches.
No, it is, see, it is like this. You start with the number of nodes that you have. Okay. And then you design the edge switches and the core switches accordingly. Now, again, here there is a proportion. If you notice here that, as I was mentioning you, if you divide this bandwidth of the edge switch exactly half between this and this, then you have a non-blocking architecture. Okay. But suppose, I mean, nothing prevents you from having 24 here and only 8 here. That will be a blocking architecture. Okay. So it all starts with the number. There are two parameters that you start with: number of nodes that you have, and whether you want a blocking or a non-blocking. Non-blocking means half of, blocking means you have to decide the ratio. So suppose it is 8 and 24, then it will be 1 is to 3. That is, 3 links will get merged into one. I hope you are getting it, right?
Yes. So
Okay.
let's
So
suppose if we want to add some node, so if we will check from any of these if 1 to 16 if any of these is empty. If it's not empty, then we'll create one another node section of 1 to 16, and for that we will need to create edge switches and also core
yes,
switches and so on.
yes, correct, correct, perfect. So if you
Okay.
want to, for block non-blocking architecture, it is straightforward because there is only one way of doing it. Okay. So it may happen that you will have to add one more switch here, then again reconfigure this, because that switch should have connectivity to all the 8 switches. So you will have to rework the whole thing. It may end up that you may not be
Yes.
able to connect 16 here if you add one more. I mean, it depends. You may have to reduce this, add number of. So there are these configurations are known that for non-blocking, what is the capacity of the edge switch, what is the capacity of the core switch, and you put it in an Excel sheet, you will get the results directly. I mean, it's that straightforward. Okay. But for blocking,
Okay.
then you have to
Yes.
decide the ratio.
Yes.
Okay.
Got
All right, so we will continue with the components of a supercomputing system and what are the programming considerations for the same. Okay. So we'll begin with the parallel computing basics that I have mentioned this in the morning also, that there are large number of problems, not all, okay, not all problems, but a large number of problems which can be divided into smaller ones. It's possible to divide it into smaller ones, smaller problem, which can then be solved concurrently. So this is the basic idea, that the problem that you have should be divisible into smaller ones, and not all problems fit into this criteria. There are some problems which are inherently sequential in nature, and it is like output of one goes to second, second of output of second goes to third, or whatever. So they are not divisible, and in which case, one example that I gave you in the morning, you want to add the to a sum, you want elements of an array, that is parallelizable because you can make them into independent tasks. But there, I mean, a problem, I'm not getting anything off my uh, mind about which could be a purely sequential problem, but you can search for it and get it that some problems are extremely unparallelizable, or if you try to force it to be parallelizable, the time taken will be more because of the way the algorithm is. So that is the first thing you have to look for, whether this is parallelizable. Okay. So once you know that it can be solved concurrently, then you use parallel processing. So you essentially make use of multiple processing element, and we saw that MIMD architecture, and through that you can do it. And also associated in this regard, we need to mention distributed computing. And this we saw cluster is an example of distributed computing. So these are the basic things on which the HPC is based on. Okay. So then what is this term high performance computing? It is a slightly broader connotation, in the sense that it has to make use of the parallel processing, what we saw in the previous slide, that is required concurrent elements and the problem should be distributed on them. Okay. So once you have that, you make use of that basic technology. On top of that, you add a few more things, and the purpose why you use this is for fast numeric simulations, modeling, and data processing. So this is very important, that number crunching is a crux of HPC. Okay, and that's what the next point says, that whichever requires mathematical calculation, weather forecasting, then computational fluid dynamics, trying out various combination, how protein will dock onto on a molecule, or all these things which needs a lot of mathematical calculation. That is the ideal thing for HPC. Okay. And the aim is that you whatever compute power is available with you, you make it to execute a few application extremely fast. So time is an essence in this. To give an example, suppose you have weather forecasting code, and you collect the data. So you collect historic data over a period of 8 days, let's say. That's how the algorithm takes, and using that, it tells the weather tomorrow. So you have collected the data at 12 noon today, the set of data is available with you, and you have an algorithm. Suppose you run it on a standard computer, you will definitely get the result, but the result will be available at, let's say, tomorrow noon, but you want to tell the result today evening 5 o'clock, so that people are prepared for tomorrow. So this first case doesn't work. So what you do is you break up the problem, run it on a supercomputer, and make it run fast. You get the results in an hour, then you visualize it or whatever, go through it, and declare the results at 5 p.m. So that is the important thing, that you want to take an application and run it fast, and that is one of the idea behind it. And how do you define a supercomputer? Okay. What is a supercomputer? So it is that performs at the currently highest operational rates. So Param 8000, the first computer that CDAC designed in the year 1991, has less compute power than the mobile that you are using today. So point we are trying to make it is a shifting target. And if you want to know which are the today's top supercomputers, then you reach out a website called top500.org. The top Indian computer, Param Siddhi AI from CDAC, appears at rank number 62 in it. Okay, so just go through that list and you will see what are the compute powers worldwide. Okay, so now let's look at how will you architect a supercomputing solution. Okay. So earlier in 80s and 90s, Cray was the first one to build a supercomputer, and what they did was every new generation was a faster and more powerful computer. Analogy is an earth moving machine like this. So let's say existing earth moving machine moves earth at the rate of 100 square meter per second, let's say. You want something which can move at 150 square meter per second. You build something with a bigger wheel and the bigger engine. You keep doing that. That was how things were, and these were not sold much, so they were very expensive. After 90s, what happened was, just as I mentioned how a cluster is, same thing you did do it. Let's say this machine can move 10 square meters per second. So now you want to move 100, you put 10 of them. So 10, so you divide the area. This is your area, divide it into 10 parts. One fellow working here. So parallelly, he has to move the earth, maybe dig the earth. This fellow can dig the earth here, this can dig here, they can move forward and back and cover the entire area. And this is embarrassingly parallel kind of thing. No dependency between two things. You just divide the work and let this each of these units do it. Okay. So that's the time when 1990s I mentioned to you about Beowulf cluster. So commodity off the shelf component, hardware, software, everything. But how do you make them work together? You use cluster, and you now know enough about them, about the nodes, about the network that binds them together. Okay. So here is an example, Cray supercomputer, custom built. So this, I think this is Cray YMP. Before that, there was XMP multiprocessor. Then there was YMP. Like this, the generation kept coming in bigger and bigger. Whereas this is Param UR2 cluster. So what is not visible here is this is one node. Actually, this is one node. This is other node, third node. So 9 nodes in a row, and 8 such rows, and then columns here. So total 288 nodes in Param UR2 connected by ParamNet, and you saw a glimpse of that in the previous lecture, and InfiniBand, 2 networks. So that is how this cluster is made. So that's the difference from 80s to 90s. So now let's look at the units or the components of a cluster. Okay. So what I showed you, what I mentioned to you in the previous diagram, these are actually these nodes, the compute nodes, 288 of them for Param UR2. Now, how do you connect them? You connect them using a switch. And for that, you use a primary network, which is shown in this green. So imagine this 288 nodes, this link goes to a switch. So that becomes your compute engine. You can run a code on it, but that is not sufficient. Where will the data and code come from? That will come from the hard disks. So that is here, you see this is a file system in all of these are hard disks. Maybe 1,000 hard disks are there here. But you don't use a simple file system like NFS, but you use what is called as a parallel file system. So what is PFS? PFS allows each of, suppose there is one very big large file. Okay. So normally you would know that if one process opens the file, it gets locked for reading or writing, whatever. However, what you can do is in PFS, you can take a file, divide it in certain sets, and one node, let's say N1, the code running on N1 will write a part of it. Code running on N2 will write a part of that file. So the areas are mutually exclusive, and the PFS allows such multiple processes with appropriate means of locking them to read and write. So what happens is you divide the task among these compute nodes. They are independently working on the data, and the data is so big that it cannot fit in the memory. So it has go into virtual memory, and virtual memory will be implemented on this parallel file system. Okay, so the code has to take care that part of the code operates on a certain part of the file, and then there should not be any bug that one process which is reading and writing into it, it encroaches upon somebody else's. So that all that will have to be taken care of. Okay, so just a minute, let me put it this on silent mode. All right, so this is how the parallel file system is required. Now this is like this is typically hard disk based, but in between that you insert what is called as storage acceleration. So this is a combination of SSDs and plus large amount of RAM. So frequently used data and code resides here, small part of it. On day one, I had explained to you how cache works. Apply the same principle here. Large amount of slow storage, small amount of fast storage. Part of it is here so that whenever the compute node need to read and write into them, it does not go all the way to this, but it gets here. So that is the storage acceleration. Similarly, this is called as compute acceleration. So what do they contain? They contain GPU. I will explain what a GPU is before we end this session. So this can do vector processing. I will explain that when we talk about GPU. Okay. So now, whenever a user, now remember that none of these nodes have got keyboard, mouse, display, etc. All that is managed through when you, and I will this is all will be demonstrated to you how we run a code on a supercomputer. So the user who is somewhere here on the local network, there is a gateway which has got firewall and other things, and from here he logs into the login nodes. Like Sucheta will show us how she can log in into 1.3 petaflop system, how she can log in into a system at IIT Kanpur, Kharagpur, which all are being managed by CDAC. So she, once you log in here, uh, you launch a job, you create a job and you launch it, and then as she will explain to you, the operating system of the supercomputer will know when a particular a set of nodes that the program needs are free, and the job will be launched. All this, hold on for an hour, all this will be demonstrated to you. Now you have so many nodes, they have OSs, they need patches, they have problems. So now you can't go and start working from each one of them, connect a mouse, keyboard. That's the last resort. So there is this blue colored wire, blue colored network. This goes to what is called as boot servers and management node. So now the OS for this in all these nodes comes from the boot servers. Why? Because you have to just maintain a copy here and say that if a request comes from N1, give this copy. If request comes from N2, give this copy. So in in uh, in one instance, all the nodes may have the same copy of OS, or you may want to have some different versions on different node. That's much easier. So it is booting from the network, not from the hard disk. And management node, they can capture the screens over. There is something called as IPMI. So I don't remember the full form. It's an interface, integrated something management interface. Okay. So that allows you to capture the screens of any of these nodes over here. So these management nodes will have proper terminals, keyboard, mouse, all that will be here. And using that, the system administrator can manage all of these. And of course, there is a tape library for backing up data, or you may get, suppose you are based in Chennai and you want to send huge amount of data here, cannot be transferred over network. You will send tape drives or something, they will be put in here, data will be loaded here. Okay. And those are the major components, and we will see a demonstration of this in the afternoon. Okay. So any questions about this?
Uh, I couldn't understand why we need a parallel file system and not the network file system. Why the network file system will not work?
See, network file system allows multiple clients to read and write into, but one file, if a file is locked for write, another node cannot, another process cannot open it. Okay, so that's a NFS is as same as your normal file system, except that it is available on the network, and it is like a server which is serving to multiple clients. Whereas a parallel file system is a file on a parallel file system is owned by a job, and a job consists of multiple processes, each process running on each compute node, and the connectivity between these nodes and the PFS is that pipe is pretty thick, because multiple streams of data, each processed by a process on a different node, they are simultaneously going in. That is a difference. So it is a network file system in that sense, because multiple nodes on the network are accessing it, but it differs in terms of, like, if you want to know more about it, look for Luster, what is our GFS. So look for them. They will that will give you an idea as to what is the difference between a normal file system and a parallel file system. Okay.
Thank you.
Any other question? All right. So let's move ahead. So now let us see how this parallelism comes in. This is an old slide. So in this, I had told you that pipelining allows, that's a basic thing which existed from the times of 8085. So parallelism is one. Then superscalar, we saw that you have multiple units. And but remember, in the morning we talked about hyperthreading. For getting best performance in HPC, hyperthreading is disabled, because we don't want much of swapping. The code is written in such a way that once a process is given to one processor, it will try to keep it as busy as possible. Okay. So this is through architectural feature. Third thing that happens is that you have this SIMD instruction. So this SIMD instruction, as I told you, they go in the execution unit. So execution unit has the vector processing unit, and in one instruction you are doing multiple data at the operating on multiple data at the same time. Now we put all these things together in a core. So what do you put inside a core? Pipelining in the execution unit, many execution unit, and each execution unit having SIMD instruction. So this is your let's say i7 Xeon processor, which has all these features. Okay, so this has gone into one core. Okay, so this is not the CPU. This is just a core, and you have, in this example, you have multiple cores inside one chip. So this thick boundary is of a chip, which is now, as the morning he said, it's called as system on chip. In a way system on chip, but system on chip has a bigger connotation, like your ARM processor in your mobile phone is a true SoC, because it not only contains the CPU, but it contains other things that are required, otherwise would have gone on the printed circuit board. So here in the simplest form, we have shown that there are two cores and a common external bus. So these two cores behave independently of each other. Now suppose this is a CPU on which you are running, let's say, Linux operating system. So Linux operating system will run on core 1 in the simplest form, and the process that it spawns, it will run on core 2. But in real life, you don't have just OS and one process, but you have multiple processes, or processes are multi-threaded. So the OS manages maintains queue for each of these cores, such that they independently, I mean, you can almost assume them to be symmetric multiprocessing kind of thing, because externally, even if you connect memory here, so like this is much simplified way. In an actual processor, the memory controller is also inside this. So cache is also here, part of cache is here, L1, L2. So not to complicate things, I've kept it simple just to make you aware that due to increasing transistor budgets, now what we have done is beyond superscalarity, beyond SIMD, we went by adding the cores. It's almost like saying you have two CPUs packed inside one physical chip. Okay, so that is the next thing, that you go from single core to multi-core. Okay, what do you do next? Then you put two such chips, and then comes the main memory. So If you had not put the second chip, this memory would have been connected to the bus interface. Okay, so remember, this is not a true picture, but it is a representative picture. So now the server motherboard that you get today is this here. So you can see here, this is one socket, this is other socket. These are the memory DIMMs. So 4 of them. So two each. These DIMMs are on the bus. Okay. And one more thing, I had shown you NUMA in the morning. Okay. So some can implement NUMA, meaning these 4 memory modules connected to this. These 4 memory modules connected to this chip, and in between a high-speed interface which is managed by the CPU. That is other way of implementing it. So it depends upon I think Thursday I had said that in answer to Adi's question, that when a chip is designed, how it is going to be used on motherboard, that is decided by Intel. Okay. So this is one representation of it. There could be other way of doing it. They have Intel has designed they have their own, I think it is called as CXI, if I'm not mistaken, which connects to CPUs. Okay.
Yes.
Yeah.
Omnipath or CXI is where it is, and Omnipath is the one they use.
So Intel decides whether this particular chip is going to be used on a desktop for personal use with only one processor or multiprocessor. How is the cache coherency going to be? Everything is decided at the time of design of the chip. So the design of the motherboard has to only decide how many SIM slots he will put, how these are the IO slot, PCI Express IO slots, how many he will put, and how many LAN ports, 2 of them, how many USB ports, 4 of them, all that. That's the only thing that the motherboard designer can do. So now this motherboard goes into a box like this, which has got redundant power supplies, and this has a provision for 3, 4 are 12 hard disks. Then these are the fans for cooling. That's how you make a node. So a node will have, in this example, this node will have 2 CPUs. Each CPU has to have 2 cores. So now in practice, you will have today, you get I think a minimum of 20 cores in one Intel processor. Minimum of it. I mean, the newer ones, I think Ice Lake, Cascade Lake, and they keep coming. It's difficult to keep track, but I mean, another one is 24. So that's this is just a number. Don't worry about that. Point I'm trying to make is this is much simplified view, but in practice, you will have a sort of, so you can see that these two are SMP, and so effectively in this example, it becomes a 4 core SMP in a way, because all of them have got a equal access, but again they have caches L1, L2, L3. So just if you can ignore them for the moment to make you understand how this architecture is. So what we have done is we had some enhancements in the code. We put multiple of them in a chip. We put multiple chips on a motherboard, and then we are ready with our now. And this, the Paramnet network interface card that I showed you in the morning, that will fit here, and the cable will come out of this. So one cable comes out of this, 288 such node, 288 such cables, they all go into one switch. That's how the cluster will be made. Okay. So now this this total height of this is about 40, we call it 42U, and this height is 2U. So there will be some space left for network switches and something, and remaining you can populate based on how much kilowatt they have, because each rack is rated for some kilowatts, so much power it can distribute. So based on that, you will form a rack like this, and these racks, now this is one rack that I showed you on the previous picture. So this one rack is actually this rack. In this case, the nodes are 4U. So 4U into 9, 36U is occupied by this node. So these are slightly older, so that's why they are 4U. If you buy one today, it will be just 2U. So 1U is 1 point some inches. So that's a mechanical standard that they use when you want to do. And this width, the standard width of this is called as 19 inch. So these are 19-inch racks. So there are guides here and not seen here. These guides have corresponding guides here. And in these guides, you just push them in or pull them out, and here you will fit it. There are screws here using which you fit it inside. Okay. So this is how you reach a cluster. So we started off with a superscalar architecture, and we ended up in a supercomputer, which will have so the total number of cores in this is in excess of 28,000 if you take all of them. So again, I'm saying this is an older one. If you were to make the same capacity as this, you may use less number of nodes, because now the number of cores, this one had 8 cores in one CPU and 2 of them, so only 16, whereas the minimum that you get today is 40. So 60 has become 40 or maybe more. So the number of nodes for the same compute power is going to reduce drastically. So putting it together, what I mentioned to you, SISD unit, single instruction, single data with pipelining, 8085, 8086 kind of thing is the basic building block. It can do one floating point instruction in a clock, very simple. So if you add multiple execution unit, you can do multiple of these. So superscalar. So not guaranteed, but every attempt is made to keep all the execution units busy all the time, but may not happen always based on the dependency. SIMD, what does it do? It increases the width of the extension unit. Uh, SISD, only one data, let's say 232-bit values. It can operate on operand A and operand B. But now imagine this becoming 512. So 512 divided by 32. So many operands at a time, right? So 2 raised to 9 minus 2 raised to 5, 2 raised to 6. So 16 data in parallel can be operated upon by the same SIMD instruction. So you not only increase the number of execution unit, you made them wider to operate on parallel data. But remember, only SIMD instructions can work on it. The data should be like that. That streaming data, audio, video, they will be using this. Not all data can use it. Then superscalar processor with SIMD support is the core, as I showed you. CPU contains multiple core. One CPU goes into one socket, multiple sockets into one motherboard, two in our case. I showed you peripheral power supply that can make it, you can make it redundant. That makes a node, typically 2U height. 42U cabinet. So many number of nodes, you have to worry about heat and power, how many you put in there. So multiple cabinets, cooling, UPS put together, then storage, that diagram that I showed you, storage, management node, then the gateway, all of that put together makes a facility. Okay? So that's how you build a supercomputer. So the next topic for us is, now that we have this hardware with us, now that we have this hardware with us, what is the software that will run on it? How will we write codes? So tomorrow Preeti will actually tell you how you write codes. Today I will only tell you what are the algorithms used, or what are the ways in which you can think of your algorithms. So now anybody has a question? I heard some noise. Yeah.
Yes.
Go ahead.
Yes, sir. So we have so many cores in this supercomputer. So we have a large program which we want to run on it, and obviously it will be divided into some processes and threads. So our first question is, who will divide this into these threads and processes, and the second question is, how will we divide it into this process?
So who will divide it? You as a program. Okay. And
So
a
we
framework.
must have some operating system, right, which will be dividing. We will giving our program to the memory. So then our operating system will be working on it, right?
So like in the demonstration, I will show you how you write a program, how you compile it, and how you run it. Okay. So obviously Linux is the operating system, and it's a lightweight Linux that runs on the nodes. Okay. So that will be clear to you. The whole life cycle of a parallel program will be clear to you when Sucheta helps us in demonstrates that to us, which we will see in the last session today, starting at 3:15. So don't miss that. Okay, so that is who does it answers that. The programmer has to do it. And how he does it, I will be covering it now. What is the philosophy? behind making that happen. Okay, and some things now you will ask how many threads should I divide it into 4, 8,
Yes.
16, right?
Yes.
So that
Yes.
is a part of that's how I will ask Sucheta if she can demonstrate that she divides it into more number of threads and the task gets completed earlier. So whether she has that lined up for us, we will see, but that can be done. Okay, so hang on for some time and that both your questions will be answered.
Yes. Okay.
Anybody else has any question? All right. So why are we to understand or to be able to appreciate how this parallelization is done? We will have to first build up a case as to why do we want parallel computing. Okay, what is that we are trying to achieve? So once we know what we are trying to achieve, then we will be able to. It's like deciding where do you want to go. So then you can decide how you want to go, what path to take, what resources to use. So the reason why we use parallel computing is we want to overcome the limitations of a single CPU system. Single CPU systems are there. You are writing codes on it. They are running, and but why? What is the motivation for going parallel? So what is the limitation? There are two limitations. First is that sequential systems are slow. Your algorithm, you think serially, you write a code serially, your data is huge, uh, it will work, but may take days, weeks, years. I mean, theoretically, it may take years based on how much data it has to crunch. And your computer is assuming that computer system will not conk and the resources are adequate, memory space and all is there, even hard disk space is there, it will work, no doubt about it. After all, it's a computer, you have written a bug-free program, it has to run, no doubt about it. But I give you an example, weather forecasting. You can't wait so long because in many cases, late data is useless data. Okay, so we can't burn up CPU time and power and then say that hey, you gave me this data, but it's of useless to me. So you have wasted time, money, and everything. So you put more CPUs. What will you achieve? More CPUs will get the job done faster, obviously. So you want tomorrow's weather to be notified, get it done in 1 hour's time. Okay. Second thing, sequential systems are small. Every processor has got a address size, like 64-bit address. So 2 raised to 64, that is the memory you can address, not more than that. But your data is huge. Data will not fit in the memory. It will keep swapping. It will go to hard disk. Keep doing that. Not a good idea. But if you give more CPUs, each one comes with his memory. So you have those 28,000 cores. Every core has got some amount of memory. So your memory becomes used. So the problem will fit into memory which otherwise was not fitting in the memory of one processor. So to sum up, you can save time, you can solve bigger problems. So now this is what we want to achieve. Let's see how we can do it. So before we get into that, how we are going to do it, we will start with an ideal situation and we will see how close can we get to this ideal situation. So you have a array of processor, a pool of processors. You can consider them as workers, like let's say a construction site, so many workers, and then each processor, each worker has a unique thing to do. Okay, and because once it's unique, then he's on his own. You give the data, give the code, it will thrash the data and give you the results. Job done. Okay, if it's unique, then really good. But normally that may or may not happen in real life. Communication among them is largely unnecessary because communication takes time. Memory to CPU bandwidth is much larger than CPU to network interface card. And then the delays, the latencies, the bandwidth, all that comes into picture. And finally, uh, all processes do equal work. Morning we saw barrier because they have to all arrive at. You divided the work, let's say among 10 workers, all 10 of them are equally fast, all 10 of them finish in 15 minutes, and then you take their whatever they have done, put it all together, and you are ready to, let's say you are making a, somebody is making a matchboxes, dipping the small sticks into glue, not glue, whatever that is, that chemical, Okay, and then putting it in a matchbox, 50 of them. So unless and you make a box. So let's say a carton contains 100 boxes. Then only when 100 are ready, you would be able to pack them. So you have distributed among 10 each to 10 workers, and 9 of them are good, and 10th one takes additional 5 minutes. What happens? The remaining 9 have to wait till he finishes, and then only then they all of them can put their things in the box, and the box can be carton can be packed. So in real life, all of them cannot do equal work. Some of them may do slightly more work, slightly less work. That depends on your algorithm. Though this is an ideal situation, and one should try to get as close as possible to this. So when you are thinking about parallel algorithms, I said that not every algorithm is parallelizable. Then these are some of the attributes that have to be present in them. Only then it will make sense to have uh, uh, parallelize them, make even think of parallelizing them. First is concurrency. If there is all serial, I mean, don't even try to attempt it. So ability to, and what I mean, we are not talking about that Amdahl's law and all. We don't have time for that. If you have time, just look for that. What does it say? A H or AMHDAL, Amdahl's law. So if you have, you should have at least more than 80% of the code which is parallelizable. Only then it is worth parallelizing. Otherwise, the benefits are not all that great. Scalability. If your processor count increases, your time taken should fall. And this is to some extent it is linear. After that, it falls off, tapers off. So as long as it can go increasing in terms of performance, reducing time to execute, that is good. Data locality. The algorithm should be such that your data should be close to where the code is running. It should not be there is a big pool and everybody is taking from it and takes time to reach the processor. Modularity, of course, this is something which any program that you design has to have it, so that you can then divide and conquer. Take a module, see what best you can do for it, and then that gives benefits to the entire program. Okay. So I will just, these are some of the mechanisms used. I will tell one by one. So phase parallel. So there are program is divided into super step. So what is a super step? Super step is a combination of compute and synchronize. So here they will compute this portion. It will compute. This is increasing time. Then they will wait. Whichever finishes barrier, they will exchange information and then again go ahead with the next set of data, then again interact. So they blocking communication or barrier blocking communication, you will study tomorrow in MPI, and that's where they exchange data if required. And good thing about it is that here they are independent of each other. Only here they start. That's how you have to. Now remember, this is what we are saying. This is the design of an algorithm. You know what task you have to do. You have to decide in which of these models is best suited for parallelizing your code. Okay. Divide and conquer. This is a well-known algorithm that you start off. This parent starts here. It divides it into child one and child two. Half of it. Child one divides it into grandchild one, grandchild two, like this, and then the grandchildren return it back to their parent, and the parent return back to the grandparent. So this is how you do it. So now here I'm showing two, it could be three or four. So this is another way. So it has been found that if you want to do a quick sort kind of algorithm, parallelize it, then divide and conquer model is best suited for it. So again, I mean, we don't have time to give examples and how it well fits into that, but here you will only know. I mean, I'm just giving you a glimpse of what are the standard methods that are used more commonly. Pipeline model. Okay. So you form some kind of a pipeline. So what is the attribute of a pipeline? Output of P goes to Q. Q does some processing, output of that goes to R. This is very similar to fetch, decode, execute pipeline that we have. But this is useful where when the data is streaming. So continuous data is coming, you are doing a series of transformation, and the data is going from one stage to another, and finally you get the output data. So some algorithms, they can very well take advantage of this pipeline model. There is a farm process model, so it's very similar to the child one, except that the worker who is given the task, he further doesn't divide. The master is the one who knows how many workers are there. The master is the one who divides the work, and the master is the one who receives it back. So master will do the coordination. It will not do any computing. It will just wait for each worker to finish, and then, of course, as I said, it's modular in nature. So you perform one module, parallelize it, then that's where you get the data that becomes the intermediate data. Then you, based on that data, you do the next modular execution, and in that way it goes on. So that this is process farm model for you. Then the domain decomposition. So this is, I mean, again, I am not an expert in software writing. Yes.
Estimator.
Yeah.
Okay, so I have just one question. Like, is this master a software or hardware?
So this is all software. So each one is running on a node. So you have
Okay.
those 88 nodes. One of them will be master. So it's a
Okay.
process. So master is a process, and as we shall see, each process is assigned to a processor, and that it will run on that processor. Okay. So one will.
Okay.
It's a role. It's a role.
Yes. Thank you.
So now there are some things which are called as boundary value problems. So again, as I said, I'm not an expert on it, but this boundary value problem is something which involves use of matrices. Okay, wherein you divide that domain, big domain, into subdomain and subdomains, and like this, and then you assign it to processors. And what happens is there is a communication between neighbors. That is the pattern that you see. So some of you might have realized that the torus topology is well suited for such kind of problems. Okay. So there is always some affinities of algorithms to networks, or algorithms to or to a particular architecture. So these are some of the things that are inherently found in some of these things. So that's how you make the best use of whatever resources you have by adapting your algorithms to the architecture, or populating your architecture with appropriate nodes that are best suited to solve your problem. But many of these computing systems like this that I was mentioning, Param Shakti at IIT Kharagpur or Param Sanganak at IIT Kanpur, they are general purpose, because in a IIT you have, let's say, 30 departments. Some is doing agricultural research, some department is doing chemical, some is doing trying to solve civil engineering problems. So you have to have a general purpose kind of thing, which is not, I would say, very optimized for a particular solution, but it is more useful for a generic program development, and scaling and all other things can be tested using that. Okay. So that is the domain decomposition. Okay. So typically, I mean, I'm oversimplified it, and one day is not enough to learn parallel programming, but just to give you a flavor of it, typically what happens is, it obviously starts the serial program, the master program, or the first program that comes in, who will distribute data to the memories of the individual processing elements over a network or whatever way, then distribute the code to them so that that code can operate on that memories, then organize the flow, barriers, and all those things. And the last thing, first you make your program run correctly. Your results should be correct. Against test data, it should generate the expected results. And then you tweak the algorithm, have a compute communication overlap. Then there are so many techniques. I don't want to trivialize it now by making passing references. So this is how one goes about it. And a small program will be demonstrated in the last lecture today. Now, how does one do it? What are the frameworks? Because you cannot be implementing the critical section, barriers, all those things. Implementing it at the user level is very, very difficult. So you use some frameworks like OpenMP that works for shared memory computer only. And I give you an example. There are compiler directive hash pragma OMP. Then the compiler understand that this is a something related to parallel. Okay. So we will not, I will just demonstrate that, but OpenMP itself can take a week to understand. MPI, this is suited for distributed memory computers. OpenMP will not work on distributed memory computers. Okay, it makes use of libraries. So it's not compiler directive based, but it makes use of libraries. So Preeti will explain this in detail tomorrow. OpenACC is used with like GPU cards you have. Then through compiler directive based, you can accelerate some part of your code. Okay. So MPI of this will be covered tomorrow. So these are the frameworks that one has to use. And there is one more, which is used with graphics processing unit. So any questions so far? All right. So let me, I had told you that in the accelerated nodes, you have accelerators. So there are various types of accelerators. One of them is a graphics processing unit. Okay. So here is a recap of what we saw over today and last Monday. That this is a single CPU system with its memory, and we saw that this is an SISD kind of computer. Okay. Then you make it SMP. You have a big memory, and CPUs can talk to each other. They can talk to memory. Okay. Then we saw the distributed architecture wherein MPI and other things will work. So these are the standard ways. But now, how do you go beyond this? Okay. There is a serial code like this, let's say. Okay. So there is for some of the libraries, there are parallel libraries available to do your speed up your mathematical calculation. And one such library is called as BLAS library. And this BLAS library has a routine. Okay. So now this has got some encoding that this is an arithmetic routine. A stands for arithmetic routine, and one is some, I think X or something represents floating point. Like this, that word has become SaxPy. Okay, so this SaxPy routine in serial form looks like this. That it takes a value of n, which is pointing to the number of elements in this array, and there are two arrays and pointers to them, x and y. And what we are trying to do is, so those two arrays, we are adding the corresponding elements of to generate the new value of x. We are adding y x to y, but x has a scale up. A is the scale up. Okay, so I think that's pretty easy to understand. So how do you invoke it? You say saxpy serial. You specify n. Suppose it is 1000. The scaling factor is 2, and you give the pointers to two arrays, and you will y will be updated after you invoke this. So y will get a new value, x will remain same. So I think that's pretty easy to understand. So if you have to do such a routine, you have just one CPU, you will start with I equal to 0, then keep doing it, one instruction at a time, I keeps changing, and your job is done. So this is how serially it will run. Now, if you have to run it on GPU that is made by NVIDIA, and the framework is called as CUDA. Okay. So that routine will always have triple underscore global triple underscore. Okay, so that is the first thing that you will have to do. Now instead of serial, it becomes parallel. Okay, then everything is same. If you see here, these values are exactly same. However, inside that, what we are doing is we have large number of cores. We have large number of cores, and a part of, so it's like this. Let's say you have, what did you do earlier? You had a two arrays. Okay, so what you said was new value of y is equal to old value of y plus a scale of x. This is what you did. New value of y was this. So now when you have a in a serial form, you CPU does this 1,000 times it does. But suppose you have 4 core. What is that you need to do? You give this to core 1, core 2, core 3 and core 4. So 250 elements each are given to each core. So how will you do that? By dividing it into threads, and each now see this is a thread id.idx.x. Don't worry about this. This is a part of the runtime. Okay, so where it has come from, if you study CUDA programming, then you will know. Here I have tried to make it extremely simple just to indicate to you that the value of I, okay, value of I is, in this case, it's going to be, I mean, it will be given, the starting value will be given. Like it will, see, remember it's parallel. So it will be invoked on 4 processors, and this is just one of them. And what is its thread index? It will give a thread index of, let's say, 0. Second one will give a thread index of 250, whatever. Third will give a index of 500. Fourth will give an index of 750. So from there it will go. And how do you invoke it? Just make it, and here you put the n value of n here, and everything else remains same. So don't ask me to explain this code, how it works. What is important to note is this, that if you have, let's say, if your n value of n is 1000, and if you have 1000 cores, then each core will execute only one of that statement. Conversely, if you have only 250 cores, then each will execute 4 instance, a loop 4 times. And if you have 4 cores, I mean, won't have, CUDA doesn't have 4 cores, it goes into thousands. Point I'm trying to make is you just divide. What will be important is, what is important is where do you draw these lines? In the one extreme, the line could be drawn at the boundary of every element, because the number of cores are more than number of elements. If the number of elements are more than number of cores, then more than one element will be handled by one core. I hope this is clear. So in von Neumann architecture, we had seen that last time. In this case of GPU, if you notice here, you have more, you will have a similar thing, but there will be more number of these processors. Each one of the GPU will have a global memory. And if you notice here, just notice this. Only one, there is only one rectangle, but here there are planes, each one of them being one core. Okay, and there is a shared memory, there is a global memory, and there is one control unit within that, within the processing unit. So this is what is the crux of it, that not just one core, but thousands of cores are available, and there are certain algorithms which are tuned for it. So here it will be like this, that CPU is optimized for serial tasks, but now we are adding cores like 20 or so we are getting. Here, if there are 20 cores here, there are 4,000 cores here. So see the difference. Now, how do you compare the two? Okay, so here you will find that depending upon depending upon whether you are using a CPU or a GPU, okay, you will be able to like this will be, sorry, the CPU silicon ALU is less. Why? Because only one is there. Okay, Control is more because instructions are complex, and whatever is remaining is used for cache. In this case, you have large number of ALUs in case of GPU. Control is slightly less and caches are much lesser. So this is an important thing, that per core, in case of CPU, the memory is much larger. In case of GPU, per core, the memory is less. That is the uh, take home message. So now let us see what are the comparative strengths and weaknesses. It has large amount of memory, very fast, large caches, but small number of threads. Why? Because number of cores are less, but they are running quickly. Why they are running quickly? Because the speed is very high and memory is also large. Okay. Then, but it is limited to number of cores. So you cannot have large number of them, just maybe 20 of them. What are the weaknesses? Read write to memories are much slower because there is one unified memory. Okay. If the cache miss happens, then getting it from the memory is slow and it consumes too much of power for the compute power that it offers. Now let us look at 2000 core GPU. Okay, here each core, if you notice there, each core had a dedicated, some part of dedicated memory. If you notice here, okay, each core had a memory. So that makes the cumulative memory bandwidth very high. Okay, so very high bandwidth, large number of compute resources, let's say 2000 or 4000 cores, and it will hide the latency because internally it has large number of registers. And advantage is that because there are so many of them working in parallel, you get high throughput. That is the important thing, and it consumes less power as compared to CPU. So thus the floating point operations per watt, for every watt of electrical power consumed, how much compute power is given. Okay, so that is much higher. But here, what are the weaknesses? The memory capacity is much less per GPU, per core. Okay, so it is much less. And per thread performance is less because the CPU runs at much lower speed, not 3 gigahertz, but 1 gigahertz. So 3 to 4 times it is slower. So that's how the two compare. Okay. So then how can we take advantage both of them? Definitely. When you write the application code, you take out the parallel part which is suited for CUDA and run it on GPU. Embarrassingly parallel, 4000 cores at your disposal. And rest of it, let it go on CPU because CPU can run sequential code faster because memory is large one, and more importantly, clock speeds are higher. Okay. So that is what it is. So I am done. So in summary, you have clusters as the predominant architecture today. I gave you the reason, commodity off the shelf, but the emphasis on building better networks. And you have methods for accelerating it further by making use of things like GPU. And GPU itself, if you want to learn GPU itself, that will be a 1 week course at the least. So we are not getting into how you write the GPU codes or CUDA code. But let us, I hope you have got a lot of flavor of what HPC is about, because we just took maybe 4 hours to take I would say a trailer of that. So, and more about how do you write programs in MPI, that's whole day tomorrow. And today in session starting at 3:15 p.m. I and Sucheta will show you how you can write a code, run it, and we will also show you some aspects of the system administration because that is an important aspect of a supercomputing system. Okay. Now questions. I hope I did not put you to sleep after a good lunch that you might have at home.
So, sir, I have a question.
Yeah.
So, So in this CPU architecture, suppose we are architecting it using the RISC-V ISA. So
Yeah.
GPU has a different set of ISA, or it is also done with the
No,
in
it is
compiler.
totally different. Its instruction set is different, and you won't write code in I mean, you can use C or C++, and CUDA has, as I showed you, it has got. I mean, it gels well with. I mean, you can write the code in Fortran also, or you can write the code in C, or you can write it C++, or there is a Python also. So many frameworks are available for CUDA, like OpenSCC. It has got its own set of primitives through which you can write codes that runs on accelerator. So there are many frameworks that are available, and using that you can write a code. So part, see, remember that if you want CUDA GPU to execute your code, the code has to see it. GPU is a card that sits on the PCI bus, so it has its own different memory. So you have to transfer the code and data to the CUDA, and then, I mean, the GPU, then it will run and give you back the results. So there is an overhead in
Yes.
that, but I haven't got into those details because we had very limited time.
So we have a whole different ISA for GPU
Yeah, but that
for
ISA is
programming in GPU.
correct. But then it's not ISA that the programmer has to deal with, because he's writing the code in higher level language. So the compiler takes care of that. So you should be aware
Yes, sir,
that
but
how many.
and it will be converted. At the end, it will be converted to assembly, right?
Yes, yes, definitely.
So
However,
yes, sir. So in that assembly, yes, sir, yes, sir.
yeah, so point I'm trying to make is you should be there are, I mean, I haven't told you, but there are things like threads, there is gangs, and it has its own set of ways of grouping them, because some shared memories across the course. So you would like the threads to be scheduled on those cores which have common memory. Then in the global memory there are some other limitations. So the structure of your program, CUDA program, has to be tuned to the architecture, otherwise it will be counterproductive. Okay, so those nuances did not discuss, neither I know about them, but that consideration has to be given, if not for ISA but for the architecture.
Yes.
Yeah,
Yes.
you are saying
So
something.
at the just like at the end we will get some assembly language program, and then according to some what we have written, it will be given to each of our processors core, and they will do their task and give back result to us.
Yes, that's right. Only thing is,
Okay.
explicitly it has to be transferred from the main memory of the CPU to the memory of the CUDA. So that's an overhead, but that's the way it is. Okay.
Okay. Yes.
Anybody else has any question?
Yes, sir. Sir, I have a question that is, it's a bit broad, but I would really like to understand. So if you look back 10 years from now, 10 years before, we used to have these top 500 lists dominated by Intel Xeon CPUs, right?
Yes.
And today, if we see Nvidia has suddenly come out of nowhere, and most of the top 500, like the upper ranks, they're dominated by Nvidia GPUs. Now, the GPU never had that much of uh, locality to allow for execution of these HPC applications, but that is my understanding. So, has the workload changed in order to make better utilization of GPUs?
See, GPUs are good at what is called as SIMD kind of thing. Okay, so they are, because there are so many cores. So if your data, I mean, if you can have the same algorithm running across so many cores, then it is tuned for it. So if you if, as the name suggests, it evolved from graphics processing unit. So graphics displays this kind of behavior, that you have a screen full of data and you want to apply same transformation to all of them. You tile the display. So there are 4,000 cores. Tile, I mean, make 4,000 tiles out of the 4K resolution screen that you have, and each the transformation is same. So let it be applied by 4,000 different cores onto 4,000 different tiles, and your job finishes fast. So this is one example. This is where the GPUs evolved from. and they are even now much suited, much well suited for video and audio kind of traffic that or of data that you would be having. And there are some kind of applications where they can't give any performance benefit, because the overheads of transferring data to the memory, processing it, getting it back. And see, for streaming data it is good because you have a pipe, you feed the through the pipe the data, and from the other side of the pipe you have it appropriately, you keep getting the data. So now as a result, the delays for transferring data into the memory and out, they get overlapped. Initially you will have a delay, but once it comes, every few whatever time that you have specified, that packets will start keep coming in because it's pipelined. So there are some algorithms, such algorithms wherein there are no penalties, because the penalties get hidden behind the algorithm that you have. So to answer your question, uh, it was like this, that the algorithm, I mean, from ages, the programs are written in OpenMP and MPI, and clusters are good for executing them. And till GPU came in, clusters, CPU was the only way how you could run your code. With GPU coming in, what they have done is they have and algorithms existed for so many years. Like there are some known grand challenge problems, and they use things like fast Fourier transforms or some basic mathematical things over which the things are built. Solving of partial differential equations. So these are known things, known things that are run on HPC, and they were CPU only kind of thing. But when GPU came in, the CPUs like thing cannot straight away go on GPU. But there are some things that are running on CPU which can be efficiently run, like typically, again repeating myself, the SIMD kind of workloads. So it is not that suddenly things have changed, things are same. But what NVIDIA has done is, through community development, they have ported so many of the existing CPU only codes to GPU only, and they are getting some benefit out of that. So that's why there are too much of push from NVIDIA side and the community, complemented by the community, that has made it reach this stage that they are in today. Okay, so any other question?
Okay. Thank you for the answer. The second question is, yeah, I hope I'm not taking too much time. Just wondering about the difference between a data center and a supercomputer.
So the elements are same. The basic elements are same. However, uh, the way the workloads are different. So a data center, let's say which is hosting a cloud service. Okay. So how programs are executed in cloud environment, you will know from Wednesday onwards. Okay. So you will still need server, you will still need uh, network, but there won't be too much of communication between those nodes, between those compute nodes, because all of them would have high throughput to the hard disk. So you will have good throughput to hard disk. Then another thing that is very important for data centers is high availability, and like a banking server, it cannot afford to go down even for a minute. So if any, so redundancy is built into it. In case of HPC also, having redundancy is good, but the software environment is such that I haven't mentioned that, but the programs are going to run for sometimes for months also. So checkpointing is inherently built in. Checkpointing is a method by which you save the state of a program that is running. And in case something fails, you start from the last known state. So which could be as back in time as maybe 30 minutes, but that has its own overheads which extends the run of the program. But if your program is going to run for 5 days, and on the fourth day suppose something goes wrong, you are not really happy if 4 days of work is to be repeated. You are okay if 30 minutes of work is lost, that's fine. Okay, so that's how the redundancy is like 24 cross 7, and built-in redundancy and paying money for that is not something that HPC system will have. But it will definitely have the compute power by having large number of cores. Here, large number of cores may not be required, but large amount of memory and other things may be required. Of course, it depends upon what application that data center or is being used for, but generally that this is the way it is. Like sometimes there are these data centers are only for YouTube like application where they are streaming media. Then the architecture of the storage changes drastically in that case, because in case of HPC it is too much of read write kind of thing. In some of the architectures it will be too much of only writing into the hard disk. Somewhere it could be only streaming. So depending upon the application, the finer things may change.